Welcome back. In this video, we are going to discuss about standard error and correction factor. Before going for standard error, let us have a clear concept on sampling distribution. What is sampling distribution of a statistic? It is a frequency distribution of all possible values of a sample statistic. Now, this statistic may be mean, may be median, may be proportion, etc. And you must have all possible values your sample may have. And how will you get all possible values? You have to collect all possible samples from that population, and those samples must be of same size. That means you have the full list of values of all possible samples, and you get the frequencies of all those possible values, and you get that sampling distribution. For example, our population is the delay at terminating station of 4 metro railway systems. The Delhi Metro recorded 10 seconds delay at the terminating station. Mumbai Metro 20 seconds delay, Kochi Metro 15 seconds, and Noida Metro 5 seconds delay. Now, these data are not real. These are all imaginary values. And there are 17 metro railway systems at the time of recording of this video. For sake of simplicity of our example, we considered only 4 metro railway systems. Okay? What is the population mean then? The population mean is 12.5. Now, let us go for random sampling. Suppose our sample size is 2. That means we take a sample of 2 sampling units. Okay? And each time we randomly choose one sampling unit, we put the sampling unit back to the population basket. Okay? So that is sampling type with replacement, right? Now the question is, what are the possible samples we may have out of this population? We may have Delhi Metro as our first sampling unit, and we write Delhi 10, and then we put this data back to the population basket. Okay? And suppose we get the second sampling unit as the same Delhi Metro. So we write Delhi 10 again. Okay? So this is one sample we may have. We may have Delhi Metro as the first sampling unit. We write Delhi 10. And the second sampling unit may be Mumbai Metro. In that case, we write Mumbai 20 here. So this may be our second sample. We may have first sampling unit as Delhi Metro and the second sampling unit as Kochi Metro. Then we write Delhi 10, Kochi 15. Similarly, we may have Delhi Metro and Noida, so we write Delhi 10 and Noida 5. Also, we may have the first sampling unit as Mumbai Metro and the second sampling unit as Delhi Metro, so we write Mumbai 20 and Delhi 10. Also, we may have Mumbai Metro as the first unit, and the second unit is also Mumbai Metro, so we write Mumbai 20 and Mumbai 20. In this way, we may have Mumbai 20, Kochi 15 and Mumbai 20, Noida 5. In this way, we may have 16 possible samples. So this is a list of 16 possible samples. See, first one is Del and Del, and we have the sample observation as 10 and 10. And we have the sample mean as 10 here. If our sample is the second one, that is the first sampling unit is Del and the second sampling unit is Mumbai, then we will have 10 and 20 and the mean here will be 15. In this way, we will get 16 possible samples from that population, right? Now, you notice one thing that you got sample mean as 10 by 3 samples. Sample number 1, sample number 12 and sample number 15. That means if you have any one of these 3 samples, then you will get sample mean as 10, and from that you may infer that the population mean is also 10, and that is very wrong, isn't it? Now look at this one. Here 3 samples, again they are showing sample mean as 15, and if you have one of these samples when you are going for random sampling, then you may infer that the population mean is 15 because your sample is telling that the mean is 15, and that will also be wrong. That means your sample mean is deviating from the population mean to some extent, right? Now here you see these 4 samples. If you have one of these 4 samples, then you will get exactly the sample mean, that is 12.5, which is matching with the population mean 12.5 here. Now, what is the possibility that you will have one of these samples which will give you the correct value of the population, right? So that is the question. Now, here we go with the frequency table. Because if you write all the sample means, the 16 sample means, the table will be larger, isn't it? That is why we have converted the data into a frequency table so that this table is having only 7 rows because 7 types of sample means are there, and against each sample mean you write the frequency over here. That means 5 sample mean appeared only once. That is why we have written 1 here. 7.5 appeared twice. That is why we have written 2 here. In this way, you see that 12.5. It appeared 4 times, right? In our previous slide, we have seen. That is why we have written 4 here. So in this way, if you write the data in a frequency table, it will take lesser space, right? Okay. Now the question is, this 12.5 appeared 4 times, and it is perfectly matching with the population mean here. Okay. Now consider this sample at the first row, that is 5. The difference between this 12.5 and this 5 is on the negative side, that is, it is minus 7.5. If you subtract the 7.5 from 12.5, then you will get 5. And it appeared only once. Clear? Now you look at this 20 here. If you get this deviation from the 12.5 to 20, then you will have this by adding 7.5. Isn't it? Again, you say, you consider this 7.5 here. The 7.5 is having a deviation of minus 5, whereas, and it happened 2 times, and on the other side, you have a deviation of plus 5. So you notice one thing, that though these sample means are having a deviation on one side, there is a compensatory value on the other side, so that both the values, they are concentrating on 12.5, isn't it? That means if you have this 5 and this 20 here, both the values 20 and 5, that gives you 25, and you take the mean, then you will get 12.5. So one side you are having a deviation, there is some element which is taking the role of compensation of that deviation. So if you consider all possible sample means without skipping any single sample mean, okay, then definitely all of them together will concentrate on this 12.5, that is the population mean, right? On the contrary, if you skip any of the sample mean from here, suppose you skip this 7.5, this sample mean, this 17.5 will have a deviation of plus 5, and there will be no one to compensate for this plus 5 on this side, right? And that will create an error, right? So this sampling distribution, what we have in hand in the form of frequency table, is our sampling distribution. Clear? Now this sample mean, what we have here, will have a mean. That means if you consider this sample mean as your data, then the list of this data will have a mean as well as variance. Now to find out the mean of the sample means, what you do, see, we have already shown here that this mean of the sample means is actually equivalent to population mean, that is mu, right? So we denote the mean of sample means as x double bar, and we have the summation of each mean, that is xi bar, multiplied by the frequency the corresponding frequency, and we add all those components and divide that summation with the n, where n is here is 16. So it will be 1 by 16, then 5 times 1 plus 7.5 times 2, then 10 times 3, and like that. And it will get 12.5 as the mean of sample means. So it is exactly matching with the population mean. See, why it is matching? I'm repeating, if you consider all the possible sample means over here, then definitely you will get the population mean. And if you skip any one of the sample means from here, then there will be one missing compensatory value, and that will create an error or a deviation. Now, using the expectation, you can have the sample mean also. In either way, you can calculate. For calculating the expectation, you need the probabilities of each xi's, x bar i's actually. So this is the probability chart for each xi. For the sample mean xi equal to x bar equal to 5, you have the probability of 0.0625. So you just have this frequency divided by 16 and you will get these probabilities. So you apply this and you will get 12.5. So in any one of these ways, you can have the mean of the sample means, right? Now, regarding the distribution, we have to talk about the distribution type of the parent population you have. If it is normal, then the distribution type of the sample will also be normal. And if the parent population is non-normal, that means the parent population is of uniform type or the binomial type distribution or exponential type like that, then also your sampling distribution will be of normal if your sample size is greater than 30. And if the sample size is less than 30 and the parent population is non-normal, then the sampling distribution cannot be specified. So what do you see here? If you can collect all possible samples from a population, then the values of the population parameters will be equal to those of the sample statistics. In this case, we have dealt with mean. You can have any other sample statistic, then also you will get the same result, right? But in real world, all possible samples are not possible to collect. For example, if there are 2000 units in the population and the sample size is 2, then the possible sample count will be 2000 squared, and that number is quite large. In those cases, we have to go for much lesser sample count and try to infer on the population parameters from the sample statistics. I hope you understand this point, why we are going for sampling. Now, this is the reason that as the sample count grows, the statistics move towards the population parameters. That means it moves nearer and nearer to the population parameters values as long as you increase the sample count. Okay? Now, we have learned enough of sampling distribution to learn standard error. Now, what is standard error? Standard error is nothing but standard deviation of the sampling distribution, not regarding population, of the sampling distribution of a statistic. The statistic may be sample mean, maybe sample proportion, maybe sample median, anything it may be. And that deviation, that standard deviation must be from the population parameter. For example, if your statistic is sample mean, then you have to take the standard deviation from the population mean. Okay. Now that standard deviation is called standard error and it is denoted by SE. So SE of x bar, this x bar is the sample mean, and this SE of x bar is a standard error of sample means. And you can clearly see that we have got this xi bar, that means sample mean from each sample, and we are taking the deviation from the population mean here. We are squaring it and we are multiplying that squared deviation with the frequency, and we are adding these terms. Now, in our example, in our previous example, we have k equal to 7 because 7 types of sample means we got. So this summation will run for 7 times as in our previous example. And then you divide that summation with n. In our previous example, it was 16, and you square root this, and you get this standard error of x bar. So in our previous example, we had this, and we have the population mean mu as 12.5. So we get this, that 1 by 16, this xi bar minus 12.5 whole squared, and multiply this term with the corresponding fi's, and it will go like this: 5 minus 12.5 whole squared multiplied by 1, this 1 frequency 1, 7.5 minus 12.5 whole squared multiplied by 2. In this way, you go up to this 7th row, and you get 3.95 as the standard error. Now, in practical, you will not have all these xi bars, okay? In most cases, you will have only one sample. Then how do you get this standard error if you do not have all those samples, right? So for a single sample of size n with a sample mean x bar, there's a single sample mean you have got because you have a single sample. That is why you are having a single sample mean now. And the standard error of that sample mean will be variance divided by n square rooted. And this becomes sigma by root n. Now, this sigma is the population standard deviation. So, is the standard deviation of population. Okay. And regarding the standard errors, what we have discussed, the standard errors have been calculated based on the following assumptions. We assume that the sampling has been done from an infinite population or from a finite population but with replacement. So, for an infinite population, you may go with replacement or without replacement, but in case of finite population, your sampling must be with replacement. Here we go with the sample statistic and the corresponding standard error. This is a sample mean, that is x bar, and we have seen here how it is going like this. So, this is a deviation from the population mean, and one sample mean, that is for x bar. In this case, it will be sigma by root n. Now, this sigma is a population SD, that is population standard deviation. We also have difference of two sample means, that is x1 bar minus x2 bar. In that case, this will be the formula, where n1 is the sample 1's sample size and n2 is the sample 2's sample size. And this sigma 1 squared is the variance of the population 1. Sigma 2 squared is the variance of the population 2. In case of proportion, we have a single sample proportion, and you can go for the standard error with this formula. And we may have two sample proportions, that is P1 and P2. And for that, this is your formula for calculating standard error. And also we have a sample median, and for that, you have the standard error for single sample mean, and you multiply that with pi by 2, and you get the sample median. Okay. Now, you notice here one thing, that whenever your sample size grows, that means sample size goes high, the standard error goes low, because in every calculation you see that n is finding its place in the denominator. Now, whenever the denominator goes high, the result goes low, and whenever the denominator goes low, the result goes high. Now, we go for correction factors for standard error. Corrections to the calculations of standard errors mentioned is required when the population is not large in relation to the sample size. That means the population size is capital N and the small n is the sample size. Now, if the population size capital N is less than 10 times the sample size, then we say that the population is not large. And the sampling is done without replacement. That means you are not having a large population based on this relation, and you have done sampling without replacement. Now, if you go for sampling like this, then you need the correction factors. So correction is done by multiplying the standard errors, what we have calculated before, by this correction factor, root over capital N minus n by capital N minus 1. Now, this correction factor is also known as finite population correction factor. For example, we had for the standard error for single sample mean as this sigma by root over n. You just multiply this with this correction factor and you get the corrected standard error for sample mean. Okay. Similarly, for sample proportion, we had this formula, we had this calculation. Now, for correction, just multiply that previously calculated value with this expression, with this correction factor, and you will get the corrected standard error. Clear? So, you apply this to other calculations also. Now, we go for a numerical. It says that a doctor who had recently been treated Ebola patients went to the hospital with a slight fever and was subsequently diagnosed with Ebola. That means during coming in contact with the patient, the doctor gets infected. Okay. Soon thereafter, a survey with 1042 random local residents found that 82% of them favored a mandatory 21-day quarantine for those came in contact with an Ebola patient. That means there was a survey, and the survey people talked to 1042 random local residents, and 82% of them favored that those who have come in contact with Ebola patient must be quarantined for 21 days. And 18% of them didn't favor this decision. Okay. Now, there are 4 questions we have to solve. First question, what is the point estimate of proportion in this case? Second question, is it reasonable to use a normal distribution to model that point estimate? Now, why we are interested in placing this problem in a normal distribution? Because in normal distribution, we have some advantage of z values. So, we are trying to find out whether this distribution, this sampling distribution is aligned with a normal distribution or not. Question number 3, estimate the standard error of this proportion 0.82 from the Ebola survey. And the last question is that construct a 95% confidence interval for this proportion P of this residence. Let us go for the first question. What is the point estimate of proportion in this case? We can clearly see that 82% were found favoring the decision. So, the point estimate, that is P hat, based on the sample S, we call this sample as S. So, based on the sample S of size n equal to 1042 is P hat equal to 0.2. So, this is the point estimate we have. It is already mentioned in the problem. Okay. Second question, is it reasonable to use a normal distribution to model this problem? Yes. Why? Because the following 2 conditions from central limit theorem are met. The first condition is independence. The observations are independent. How do you come to know about that? Due to simple random sampling. Now, the second condition, the success and failure condition. What this says, n times p must be greater than equal to 10. Also, n times 1 minus p must be greater than equal to 10. Now, what is n here? N is 1042. This is n. And what is p? P is not available. We have p hat as 0.82. In this case, you can use p hat in place of p since it is not available. So, p hat you write here in place of p hat, you write here 0.82. So, you multiply this 1042 and 0.82 and you will get 854. Also, 1 minus p hat, if you multiply this 1042 with 1 minus p hat, that is 0.18, then also you will get 188, which is much higher than 10. So in both the cases, we have found that the values are coming much higher than 10. So we can say that the success and failure condition are met. So a normal distribution can be used to model this point estimate. Third question, estimate the standard error of this p hat equal to 0.82. We saw in the previous slide that standard error of proportion is single proportion is p times 1 minus p over n and whole square root. So in place of p, we are writing 0.82, and in place of 1 minus p, we are writing 1 minus 0.82, and this 1 minus 0.82 is actually 0.18. So you have this 0.012 as a standard error of the estimated proportion. Next, the last question, construct a 95% confidence interval for p, the proportion of the residents. Now you see that it is told that 95% confidence interval, Ci at 95, that is confidence interval at 95% is point estimate plus minus z, z star, that is a z value, times standard error. That means some deviation. So this is a deviation, and this deviation is on the left hand side of this point estimate, and the same amount of deviation on the right hand side. That is why it is plus and minus here, right? Now that means we are trying to find out the lower limit and upper limit. That's the range within which the point estimate will lie. Okay, and that range is with 95% surety. Now look at this normal distribution here. You don't have to consider this 34% here. And look at this figure. This scale is the z scale, and 0 in z scale is the mean in raw scale. Okay. Now, on the left hand side of this 0, we have this minus 0.99, and on the other side you have plus 0.99. There is a z value, and within this range you will have 68% of the data. You are sure of that. Next, within this range, that is minus 1.96, and on this side you have plus 1.96. Within this range, you will have 95% of the data. And between minus 2.97 on this side and plus 2.97 on this side, you will have 99.7%. As well as if you see the green one, that is between minus 2.58 and plus 2.58, you will have 99% data. Now see the question, we are asked to go for 95% confidence. Okay, so we will consider the range between minus 1.96 and plus 1.96. Clear? But these are z values. Now your point estimate is in raw scale. So this one is in your raw scale. It is not in z scale. It is in raw scale. So you have to convert this 1 plus minus 1.96, this deviation and this deviation from here and from here. Okay. So these two deviations, you have to convert these deviations to raw scale. Okay. Then only you can add the values to this point estimate, isn't it? So see this table. You have already got this standard error as 0.012. What is the meaning of this? The meaning is that one standard deviation, that means one z, is equal to 0.012 in raw scale. So 1.96 in z scale will be equivalent to 1.96 times 0.012. It is a simple unitary method. Clear? So we write point estimate 0.82 plus minus 1.96 times 0.012. And this will convert to raw scale. Clear? So we get this range. Let me clean up. So this is the range we have got. 0.796 on the lower limit and 0.85844 on the upper limit. So within this range, the 0.82 is residing. Clear? The result says that we are 95% confident that the proportion of the local residents who supported a quarantine for those came in contact with an Ebola patient was between 0.796 and 0.844. So in this way, you will interpret this result. Clear? We will go for one more example, and this time we are going for standard error between two sample means. So previously we dealt with a single proportion. This time we are dealing with two sample means. Okay. So we have a car factory here, and we got the data of the workers of this car factory. And the mean height, that is mu1 means the population. That means we are considering all the workers of this car factory, and the mean height was 68 inches. The standard deviation of workers, the mean height, that is sigma 1, was 2.3 inches. And we take a sample from this car factory, and it is N1 is 35. Similarly, we go with the TV factory on the right hand side, and we have this mean height mu2 as 65 inches. Standard deviation sigma 2 is 2.5 inches, and we have a sample size N2 as 50. Now, the question is, what is the probability that the sample mean height of workers of a car factory, of this car factory, is at least 2 inches greater than that of TV factory? That means it goes like this. Probability of x1 bar, that is the mean height of the car factory, is greater than equal to x2 bar, that is the mean of the TV factory, plus 2. Say at least 2 inches greater. That means 2 or more. That is why that if you go for plus 2, then it will be exactly 2 greater, and it may have more. That is why we have given the greater than sign, right? Now, if you take this x2 bar on the left hand side of this inequality sign, then it goes like this. Probability of x1 bar minus x2 bar is greater than equal to 2. That means the difference between these two means is greater than equal to 2. So our sampling distribution will be x1 bar minus x2 bar, and this difference is our data point now, because we are dealing with two populations and we are having two sample means. That is why we are not interested in single x1 bar or x2 bar, and we are trying to compare between these two sample means. That is why the difference matters to us. And we consider and we assume that this difference follows normal distribution. Always try to find out whether it is following normal distribution or not. It will be much easier for you to calculate, right? So we are sure that the difference is following normal distribution. How we come to know that? Because we see that N1 and N2 is much larger than 30. So this is one criteria we talked about some slides back, that whenever you have a larger sample size that is greater than 30, then you can say that sample is following normal distribution. Okay. Now, what we have to do in the previous example, what we dealt with there, the confidence level, that is 95%, was given to us, and we were trying to find out the raw data, that is raw scale, the data in raw scale, right? That is the interval. Here, just the reverse. Here, we have to find out the probability, and we have been given the raw data. Are you getting the point? So in the previous example, we are converting the z-score to the raw score, and here we have to convert the raw score to the z-score. So left hand side is having x1 bar minus x2 bar. So this is the LHS part, left hand side, and this one is the right hand side, that is 2. So we have to convert these two to z-scale. Okay. So let us go one by one. First, we go for this left-hand side, that is x1 bar minus x2 bar. So what is the z value of x1 bar minus x2 bar? So the formula for the calculating the z value is the data, that is the observed data, minus mean by standard deviation. Now here the data is the difference. That is why we are writing x1 bar minus x2 bar as the data, minus mean, that means expectation of x1 bar minus x2 bar, and the standard deviation. And the standard deviation in this case is our standard error. So standard error of this difference. Clear? Now, in 2 or 3 slides back, we saw that the standard error of the difference between two sample means goes like this. Okay? So root over sigma 1 square by n1 plus sigma 2 square by n2. So I put this here. So this is the formula. And sigma 1 is 2.3. So we put it here. And here 2.5 is a sigma 2. We put it here. We have n1 as 35. Here is 35. n2 as 50. So here I give 50. And we get 0.526. So the denominator is, this one is 0.526. We have got it. In the numerator, we can go for the expectation. This expectation is mu1 minus mu2. Because in some slides back, when we are discussing with sampling distribution, we saw that whenever we have the expectations of all the means, then actually we were dealing with population statistic. So here also we go like this, that expectation of x1 bar minus expectation of x2 bar, this gives us mu1 minus mu2. Clear? So mu1 minus mu2 is 68 minus 65. Here you have, this is mu1 and this is mu2, and you get 3. So this part is 3. Yeah. So we write x1 bar minus x2 bar minus 3 by 0.526. So this is the z value of this this expression, this difference. So you see this table, the z value of this x1 bar minus x2 bar is x1 bar minus x2 bar minus 3 divided by 0.526. That means you are subtracting 3 and you are dividing that difference by 0.526 and you get the z value. So the same thing you can do for the 2, which is on the right hand side here. That is 2 minus 3. You subtract 3 from 2 and divide that difference by 0.526 and you will get the corresponding z value of 2. So probability of this one becomes this one as a left hand side and this one as the right hand side. Now the left hand side, this one is actually z, and you can clearly see that 2 minus 3 by 0.526, if you get this, then it will be converted to 1.9. It will give you minus 1.9. So ultimately this problem has been converted to this problem. This is a problem in the form of z. Now look at this figure. This is a normal distribution in z scale, and this 0 is the, in z scale, is actually the mean in the raw scale. Now suppose this minus 1.9 is standing here. So the probability of z greater than equal to minus 1.9 is the green region, including this minus 1.9, this data point, because it is given greater than equal to minus 1.9. That means this whole green region. So this will give you the probability. And the red one, which is below minus 1.9, without including minus 1.9, will be like this. So probability of z less than equal to minus 1.91. So this is the point, 1 point on the left of 1.9. And if you consider the z table, you will find that the probability of z less than equal to minus 1.91 is 0.02807. So this is the figure that is printed in the table. So we go for this 1 minus this red region, and this 1 is a probability, total probability. So 1 minus this red region will give you the green region, and that is 0.9713. So this is the probability, that is almost 97%. There's a chance that the mean height of the workers of car factory will be 2 or more inches greater than those workers of the TV factory whenever you go for a sample. That's all in this video regarding standard error. We will have detailed discussion about sampling distribution in a separate video. If you find anything unclear in this session, you may write me in the comment box. I will reply. That's all.